Hello, welcome to Pipeline Integrity, Gamma Exponent Model Validation, Part 2. My name is Colin Scott. I'm a pipeline integrity engineer based out of Calgary, Alberta, up in Canada. Today's topic is going to be looking at my Gamma Exponent model, and I'm going to be doing some validation work here for axial stress corrosion cracks. If you've seen video number 1 in this series, I looked at single, individual axial cracks, either laboratory machined flaws or natural flaws such as hook flaws and fatigue cracks. Here we're going to be looking at axial stress corrosion cracks. And these are a little bit of a different beast because stress corrosion cracks tend to form in colonies, which means that you've got multiple parallel cracks. And the important thing there is to know that those multiple parallel cracks actually have a shielding effect against each other. And the overall stress intensity factor for those cracks is actually lower than you would expect it to be. So I'm going to walk through GEM validation for the axial stress corrosion cracks and give you a little background on why we need to do a bit of an adjustment here. So if you've seen my first video, you know that the Gamma Exponent model here is sort of loosely based on the original log secant model that was made by the NG18 committee at the Battelle Institute in Columbus, Ohio back in the 1970s. The big difference with the GEM model is that it's not based mathematically on length, as the original models were. This has been re-derived with a focus on depth, and that means that there are a couple of critical differences that I've made, and so far the validation work seems to be showing that it's an improvement over the original log secant model. So starting from the left, we have a remaining strength, and that's the predicted failure strength over the flow strength, and then there's the remaining ligament to the gamma exponent term, 2 over pi term, arc cos exponential. The k-squared is the material toughness. We've got a 10 factor in there. A is the crack depth, and we've got a flow strength there. Now, the gamma exponent is defined as the minimum of the crack length divided by the radius of the pipe. But that only goes up to a maximum of 1. If you've seen some of the other videos I've got when we work with localized corrosion, the limit is 1/2, but in the case of the cracks, it's 1. There's quite a bit of fine print for this model, nothing too serious. We'll walk you through it just so you've got a sense of what you can and can't do with this model at this time. Essentially, the derivation was a flat plate solution, so it's really only applicable to thin wall pipe at this point. I've come up with a somewhat arbitrary d over t of over 20. All the validation work that I've done has been using a flow strength where it's defined as yield strength plus 69 megapascals or 10 KSI. That's fairly standard. I did not go messing around with the other flow strength definitions. The flaw depth can be modified by a pi over 4 factor to approximate a semi-elliptical profile. So I'll do that for both fatigue cracks or for stress corrosion cracks that are expected to have some curvature in them. I've developed a level 2, what I call the ELM algorithm, that can be used for more refined failure pressure predictions if you've got a full flaw profile. I've only been able to validate that on metal loss flaws, so I'm not 100% sure that it's valid for cracks, but I'm guessing that something should be doable along the same lines as that level 2 algorithm. I'll also say, and this is particularly important for this video, is that the flaw depth can also be modified to account for stress corrosion crack shielding effects. So what I'll do is I'll use a 0.63 factor if I'm doing some sort of study where I would like to predict some hydrotest failures. Or I'll use a 0.84 factor if I need to be a little bit more conservative and I'm concerned with a service failure in the pipe. Some more fine print. As I mentioned, if you're doing some localized metal loss work, I limit the gamma exponent to 1/2. There is a reason for that, but you have to dig through all the mathematics of my ASME journal paper. The toughness I use for the validation is the lower bound Wallen-J Sharpie correlation, or you can use alternately, if you've got a CTOD type toughness, you can use the J equals M delta yield strength with M equals 2 for plane strain conditions. I have to be very clear that I do not recommend the Sharpie over area correlation. There's a reason for that. You have to find my other video series, which is called Pipeline Integrity, Things That Make Me Go, video number 4. That explains it, but please don't use the Sharpie over area as a lot of people would. I've done some circumferential flaw work where the tests have been done under bending conditions, and in that case I have to come up with a bending correction factor. That's actually going to be the topic in video number 4 of this series, and that's really a work in progress. And then I'd also say that the gem is not recommended at this time for cold welds or grooving corrosion. I don't have the correct data that I would need to do a good validation of that, so please hold off on that. So the depth correction factor for the gem for the stress corrosion cracks is a very, very simple thing. You say to yourself that the effective depth of the crack is equal to 0.84 times pi over 4 times the maximum crack depth. Now, the pi over 4, as most people watching a video like this would be familiar with, will approximate a semi-elliptical flaw. That 0.84 factor, I did not just sort of pull that out of thin air and throw it in there and it seemed to work. That's actually derived from some classical stress intensity factor solutions. It's a little bit complicated, so I can't tell you about it right now. It would take too long, but I am planning another video where I can demonstrate that that 0.84 factor does actually have a legitimate, I think, technical rationale. But for now, we'll just go with put in 0.84 if you're worried about a service failure and you need to be conservative, or you can put in a 0.63 if you're just, say, planning a hydrotest program and you'd like to be able to predict how many failures you're going to expect. Now, I've got 2 references for industry failure data. One is Rothwell and Coote, a critical review of assessment methods for axial planar flaws. And that's from a conference back in 2009. My second reference is Davies et al. Burst testing in pipes containing stress corrosion cracks, and that's from the PPIM conference in Houston earlier this year. One thing I've struggled with in doing this work is that there does not seem to be a lot of stress corrosion cracking data out there that's publicly available. I think that there are certain groups in industry that have those numbers, but they keep them fairly close to their chest. I'd certainly be open to rerunning some of these analyses if anybody wanted to donate their spare data to me. Right now, I only end up having 9 data points, which is statistically not really great, but it does show some interesting trends, and I think it gives me confidence that the GEM model is developing in the right direction. So here's the simple validation plot. On the y-axis, I've got the GEM predicted failure strength. And bear in mind that includes either the 0.63 or the 0.84 factor, and it includes the pi over 4 factor to approximate a semi-elliptical flaw. So that's the y-axis. And then on the x-axis, I've got the true measured failure strength. So those are the numbers that I would have got out of the reference where there actually was a failure, either in service or during a hydrotest program. Now, you'll see that I only have 1 service failure, which is, well, I guess it's good that there's only been 1 service failure, but statistically speaking, I really can't say a whole lot about that number. It's pretty good in that it's pretty close to my unity line, but it is a little bit non-conservative. This is one of the reasons that I'd really like to get some more data so that I can really see if that's a real effect there or whether I need to put in an extra correction in my model. When you look at the other data points from the hydrotest failures, you find that the agreement to the model is actually, it's pretty good. When I put a trend line through there, I see the slope there of y equals 0.91x. So that's telling me that the model is overall about 9% conservative, and so that's actually pretty good. I'd love to have more data points to see if this is legitimate or not. Obviously, if I got more data points, it might push that curve up or push it down, or who knows what. But for now, it looks like things are in pretty good shape for the stress corrosion cracking. If I look at the hydrotests, where I've got the depth correction factor of 0.63, that tells me I've got an accuracy of 1.06. So I've taken those failure ratios where I've got the true strength divided by the predicted failure strength, and I've sort of inverted from the plot there, and I come up with a number of 1.06. The precision on there, based on a standard deviation of the failure ratios, is 0.16. So that's actually pretty good. I know I'm a little bit conservative, but the precision so far has been pretty positive. For the single service failure I've got with the 0.84 correction factor, I can really just say that the accuracy on that one number is 0.85, meaning that I'm about 15% non-conservative and unsafe. So obviously that's not good, but I really need more data to determine whether I need to make an adjustment on the gem model or whether that's an outlier data point. If you're interested in this stuff and would like to see a little bit of further viewing, I've put together some more videos for my YouTube channel. I've got 6 videos that are titled Pipeline Integrity, Things That Make Me Go, and that video series is basically a critique of the NG18 based assessments that are used for both corrosion and cracking. The NG18 equations originally were mathematically focused on flaw length rather than flaw depth, and that means that those equations are pretty much wonky when you're looking at surface cracks and surface corrosion. I'd also like to point you towards the other 5 parts of this video series on gamma exponent model validation. There I'm looking at a variety of different flaw types, axial and circumferential surface cracks. I'm looking at corrosion and metal loss, and axial through wall cracks for leak rupture boundary analysis. So please dig around if you're interested in this stuff, and you'll find that all these other flaw types match up fairly well with the gem as well. If you're interested in reading some peer-reviewed papers, I do have some real work that you can look at. The mathematics behind the gem is a little bit complicated, and if you're mathematically minded like I am, I suggest you dig around and try and find ASME Journal Pressure Vessel Technology. That's the paper that goes through all the mathematical aspects of the derivation. If you've made it this far, thank you very much. I appreciate your time. I hope that you've learned a little bit here, and hopefully you're interested in model development, and we'll go on to look at some of the other parts of this video. As I mentioned, the other flaw types can also be validated against the gem, and so far I'm seeing some pretty positive results in what's going on here. So until later, thank you for your time.